And our speaker will be Anthony Janetos. Good morning.
Thanks very much. Could I have the first slide? What I would like to talk about today, and thank you for the opportunity to speak, is the first decadal survey that has been done for earth sciences and applications. Can I have the next slide, please? The vision for this study was and I'll simply read it to you. It's understanding the complex changing planet on which we live, how it supports life, and how human activities affect its ability to do so in the future. Is one of the greatest intellectual challenges facing humanity. It is also one of the most important for society as it seeks to achieve prosperity and sustainability. Let me just pause for a moment and tell you something about some of the background for the study and something about the participants, if I could have the next slide. The background, this study was commissioned by NASA, NOAA, and the U.S. Geological Survey. Its charge was to recommend a prioritized list of missions, observations, and supporting activities to support national needs for research and monitoring of the entire Earth system during the next decade and beyond. This was the first decadal survey that's been done for the Earth sciences, it was governed by a steering committee of 18 members, composed of 7 thematically organized study panels, each of which had about a dozen members or so each, ranging from an overall panel on earth science applications and societal needs, which I was fortunate to chair, ranging to land use change and ecosystem dynamics, weather, climate variability and change, water resources and the hydrologic cycle, human health and security, and solid earth, hazards, resources, and dynamics. Can I have the next slide, please? The objectives for each individual panel were to identify general needs and opportunities for spaceborne observations to advance our science over the next decade, to propose programs or missions to meet those needs, to rank those missions in priority order, describe each one in terms of its scientific payoff, cost, and potential benefits, identify observations that could not be made from space but would be necessary to complement those observations, and to identify and comment on other essential components, everything from data management to power supplies, technological challenges, and management objectives. The executive committee was, in one sense, sort of a marvel of interdisciplinary scientific interaction. Rick Anthes, president of UCAR, and Barry Moore, then at the University of New Hampshire, co-chaired the committee. We had atmospheric chemists, we had technical experts in remote sensing technologies, we had university professors, we had people from operational weather forecasting centers, we had people from the national laboratories in a very wide range of disciplines. All of the executive committee, many of the panel members had extensive experience both as principal investigators and in some cases, such as my own case, I had a decade's worth of experience working at NASA headquarters in the Earth Science program. The elements of the study task statement were first to review the status of the field, develop our own consensus on some of the top scientific questions, to focus environmental observations, taking into account a whole series of users of information and data in addition to the scientific community, and then make our recommendations. Next, please. These are the combination of the scientific and societal imperatives that we identified. The importance of understanding climate change and its impacts, certainly one of the greatest challenges, both scientifically and from a sustainability standpoint in today's world. The critical components of understanding ice sheet, sea level, and ocean circulation as a rapidly changing part of the physical climate system. Changes in precipitation and water availability, both for its scientific necessity for understanding the physical climate system, and of course, for the societal need of understanding where water will be available, not only today, but where it is likely to be available in future decades. The issue of transcontinental air pollution and both generation and transport, chemistry and transport, changes in the response and indeed the location of a whole variety of ecosystems in response to changes in climate, the critical nature of human health responses to climate, and the importance, both societally and scientifically, of understanding extreme events, both their location, their magnitude, and their frequency, in both the Earth system, the geological system, and in the climate system. Next, please. This is the first decadal survey for these communities, and was tremendously challenging. A huge organizational challenge was how to cover all the relevant scientific and application themes, as well as disciplines. It might have been useful in retrospect to have had additional panels focused on disciplines, in addition to the way that we were organized, but that perhaps will be something that a subsequent decadal survey may find useful advice. There are a large amount of multi-agency issues to confront in such a study, in which we wrestled with. This was a set of recommendations not just for NASA, but for the operational programs in NOAA, and for the growing role of agencies such as the USGS. And thirdly, there were important changes in our baseline assumptions during the study. The budgets for Earth science during the period of this study declined quite dramatically. The NPOS program, the interagency program between NOAA, NASA, and the Department of Defense went through what we could only describe as a debacle during this time period, from which it is really only beginning to emerge. We actually issued 2 reports. Our first report was something that that our panel, or our committee, and the NRC decided to do. This was issued when after we had been working for about a year, I think. This first bullet is a quotation from the report. It's perhaps the strongest statement that I've ever seen come out of an NRC committee that I've had the pleasure of serving on. Today, the system of environmental satellites is at risk of collapse. I wish that were hyperbole. It was not. Since that time, and between then and for about 2 years afterwards, there were more delays, descoping, and cancellations of missions, both at NOAA and NASA. In the final report, what we recommended were a set of 17 missions phased over the next decade, and I'm going to come back to this in just a minute, intended in part to restore U.S. leadership in Earth science and applications from space, averting the potential collapse of the system of environmental satellites on which we depend, both for scientific insight, for a whole range of societal needs, and in fact, for many operational purposes as well. We tried to represent this as an integrated suite of missions. We took recommendations from the panels. In fact, we had done a very large call for ideas and proposals. We had recommended to us well in excess of 100 potential measurements and missions. We worked for about a year on trying to identify what we thought were the most important of those. We sequenced those missions. We tried to match our sequence to the overall cost of that sequence to a combination of anticipated resources plus what we felt was reasonable growth in the Earth science observation programs. In so doing, we also took some pains to maintain the highest priorities, although I will say not all the priorities, of each panel. And then at the end of this, what we tried to do was issue some guidance on how to handle the inevitable budgetary or technology development problems. I have the next slide. Next slide. This is an overarching recommendation from the committee was that the Office of Science and Technology Policy, in collaboration with the relevant agencies and in consultation with the scientific community, should develop and implement a plan for sustaining global Earth observations. It should recognize the complexity of differing agency roles, responsibility and capabilities, as well as some of the hard lessons that we've learned, both from, for example, the Landsat mission, the suite of missions around the Earth observing system, and NPOS. Next slide, please. For currently planned, what at that time were currently planned observing systems, we had two key recommendations: launching a global precipitation mission by 2012, obtaining a replacement for the Landsat 7 data before 2012. This is also known as the Landsat Data Continuity Mission. We also recommended that NASA continue to seek both cost-effective and innovative means of obtaining land cover change information. I have to say that this had particular relevance to me because during my career at NASA, I had the privilege of being the Landsat 7 program scientist. Next slide, please. Next slide. For NOAA, we recommended in particular an increased investment in putting research results and research observations in a truly operational program. Initiating missions for vector ocean winds, for GPS radio occultation mission, and for ensuring that we had total solar irradiance and an Earth radiation budget instruments restored to NPOS. For NASA, out of our 17 missions, we identified 15 in categories, in a sense, in budgetary categories, but that are also phased in time. Next, please. I'll show you the spreadsheet of the missions in a minute. There's clearly not time to go through each one in detail. Let me share with you some of our additional recommendations for what are essentially managing such an ambitious Earth observation program. Several are related to technology development. NASA is going to have to continue to invest in both mission-focused and cross-cutting technology development to both decrease risk in missions and promote cost reduction across multiple missions. We strongly recommended that a new venture class of low-cost missions be created to foster innovation and to train future leaders. Many of us, in a sense, grew up scientifically in the space program during a period in which it was essentially necessary to bet the major fraction of one's research career that a mission would succeed. Such a model is not, in fact, sustainable in the long run and an inherently risky business. And the original programs that were instituted to, in a sense, get out of that bind saw mission costs increase to the point where they were essentially as large as the previous large missions had been. Next, please. Secondly, to manage technology risk, what we tried to do was sequence these missions according both to budget risk factors and our assessment of their technological readiness. And that at this time, particularly for missions that we felt to be more challenging, which we then pushed to the right, that there needed to be technological investments made in order to try to reduce technological risk of those missions succeeding. If it turned out that there were insufficient funds to execute the missions in those timeframes, it will still be important to make advances on the key technological hurdles and to establish that readiness through documented technology demonstrations before mission development phase. Next, please. Third, that we should leverage international efforts. Earth observation clearly does not occur in a vacuum. The Europeans, the Japanese, the Brazilians, and Chinese have active programs in Earth observations. And it's particularly important to leverage those efforts. There have been many successful examples of this in the past. Topex Poseidon, for example. Our recommendation in this domain was to restructure or even defer missions if international partners themselves select missions which meet most of the measurement objectives. But if that is done, that it is critical then to establish data access agreements and establish science teams, which has not always been done in the past. And where appropriate, if an international partner identifies missions which meets our requirements, it may be effective for NASA to offer cost-effective additions to those missions. Next, please. We've heard the opinion of some since the study was published that the recommended budget envelope was outside the realm of practicality. In fact, the recommended budget envelope was essentially a return to the investment that NASA was making in Earth science observations around the year 2000. The notion that the United States cannot afford to have the same investment in critical Earth observations that it had a decade ago was a conclusion that we rejected. Nevertheless, this is the real world we live in, and there will always be budget pressures. And so what we tried to do in our programmatic recommendations was give some guidance to NASA and, in fact, to NOAA about how they ought to respond in the inevitable world that there are budgetary pressures, technological challenges that turn out to be more expensive than one could easily anticipate a decade earlier. First, by canceling missions that substantially overrun. Second, by maintaining a broad research program under reduced agency funds by accepting greater mission risk rather than by descoping mission and science requirements. To aggressively seek both international and commercial partners to share mission costs. And rather than evaluating mission by mission, the classical way of dealing with risk, to reevaluate the set of missions periodically. And in so doing, not doing this strictly as an agency activity, but by seeking broad input from the scientific community when that is done. I won't pretend to go through each of the 17 missions in detail. We've got everything in here from backscatter radars, to GPS radio occultation, to much more complex and challenging missions using with laser altimeters and in the far future hyperspectral spectrometers for a wide variety of scientific needs. If I could have the next slide, however, rather than go through this. For each one of these missions, however, in the decadal survey, we've tried to do several things. And one is provide a detailed description of both the measurements, what we could anticipate in terms of instrumentation, what we could anticipate in terms of mission cost, and how one would use the measurements from each of those missions how they might be used to address both scientific challenges and challenges related to the societal benefit areas. Next slide, and this is my last slide. And then in addition, for each of the societal benefit areas, how the suite of missions, if implemented, could be used scientifically and in some cases operationally to begin to address those challenges. So let me stop there. There's a series of backup slides. The study was published the year before last. The initial response, both in Congress and in the agencies, was, I think, fair to say, quite positive. There have clearly been challenges in implementing it, both programmatic challenges and budgetary challenges. But several of these missions have already been selected for study, development, and the early stages of beginning to be ready for flight. Thanks very much.
Thank you very much. And before we take a couple of questions, I should acknowledge that one of our colleagues, Sally Wright, I think has joined us by teleconference. Sally, are you able to hear us?
Yes, I am. Can you hear me, Norm? I appreciate the opportunity to join you, if only by phone.
Terrific. Sally, thank you. And if you have any questions, please feel free to speak up. In fact, we'll give you first shot right now if you had anything you wanted to ask.
Actually, I don't, but I do want to thank the speaker. I thought that was a very, very interesting presentation on an extremely important and relevant topic.
I had a question I wanted to ask, and that would be, could you indicate to us the importance of human space flight in terms of the things you talked about? In
the discussions of the committee, We did not focus on primarily on the role of human spaceflight or the potential role of the ISS. There has been a tradition in the agency, not always for imagers, but for other types of measurements, of actually, in a sense, using the shuttle as a vehicle for doing launching pilot demonstrations. It's particularly true for some of the atmospheric chemistry missions and for the laser altimeters, where in a sense, what was turning out to be a regular or quasi-regular access to space was useful for doing these kinds of pilot demonstrations.
Are there other questions? Chris?
Thanks, Norm. I should have said when the last speaker spoke, just to thank all the science speakers today. Because of the pace of this committee, I know that all of you have had to come here on short notice and put together presentations. So it's really an impressive job that everyone's doing. In 2005, there were a lot of reports in the press about cuts to the Earth observing budget, putatively driven by human spaceflight overruns or needs for growing budgets. I was struck that your group didn't identify any important missions that human spaceflight would enable, and it sounds as though you didn't focus on that question. I guess I have three questions. The first is that because your group simply didn't consider it likely that there would be very high priority missions that would be enabled by human spaceflight? And two questions. That and then my second question is, and as I said to the last speaker, don't let me put words in your mouth. Should we take away from the fact that you identified 17 missions and none of those have any important dependence on human spaceflight? Should we take away from that the single biggest thing we need to make sure with respect to Earth science observations is that human spaceflight not eat your lunch? Because we could make a recommendation that there be a firewall, and that the single most important thing is that human spaceflight do no harm in this realm.
I don't think you're going to find that quote in the report. I will say, and I think as with the previous speaker, these are my words, not the committee's words. The period of greatest progress, both scientifically and programmatically, for the development of the Earth observing systems that we have, essentially came during a time when there was such a firewall. I take away from that the existence of that firewall is critical for the continued development, implementation, and in fact the programmatic sustainability of a system of measurements on which in fact we depend and will continue to depend.
We have time for one more question. Leroy?
Yeah, kind of just to keep on the topic of human spaceflight and Earth observation, as I'm sure you're well aware that astronauts take tens of thousands of photos. In fact, on my ISS mission, I took over 16,000 photos of the Earth. And we're told by scientists when we come back that those photos are appreciated and in many times, specifically targeted cases, could not have been done better by a remote sensing satellite. And so, there's a little bit of a disconnect here, and I wonder if you could comment on that. Was it, again, kind of repeating what Chris just said, is it that you just didn't look at that element, or are we being flattered and our work really isn't that important?
Let me see how to say this, because some of my best friends have taken those photos. The photos, the photography is important. It's a visible means of it's a set of information that is important for public acceptance, for getting a visual sense of what is happening. In terms of actually doing quantitative analysis, it is, I think, marginally useful. The ISS is in fact not a very good platform for consistent quantitative observations of the Earth's surface. It's not stable enough. ephemera are not as well known as they are for the robotic platforms. It has because of the orbit, you can't actually see the whole Earth. And so for many of the applications on which the community, both the scientific community depends and on which the operational communities depend, it would not be the first choice. It's not to say that opportunistic observations from that platform don't have a role. I think they do and they could. But what we were really trying to do was identify the set of missions that we could not, that in our judgment, we could not and should not do without.
Thank you very much for your
Thank you.
comments. We appreciate it.